Okay, you convinced me. Here's part 4. Alright, I want the altitude from Q to FP. Alright, so that's supposed to be a perpendicular line that starts here at Q and runs perpendicular to the side containing FP. You can tell by, if you had a line that was kind of going into this way into the triangle, there's no way that's ever going to be perpendicular. So the only way to make that happen is to get a line that comes outside the triangle bit. So the first thing you want to do is take your ruler. I'm going to cheat because it goes much faster and it's much more accurate. You'd use your ruler to make a line that's to basically extend line FP into the zone where, I'll use the ruler to show you this, where there might be a line that is perpendicular. Something like this. There's going to be a line from Q to this line. It's going to have to be perpendicular out here somewhere. Okay. If I asked you to make an altitude from F to QP, it would have been a lot easier. That would have gone this way. It could have been perpendicular inside the triangle, and the line's already there. It's kind of nice. So really, I need to ignore the QF and the QP. They're just kind of in my way. I'm really just focused now on point Q and this red line here. Alright, so the only way we've ever been able to make perpendiculars is if we had a a little segment, and then we could make a line that's perpendicular to that cuts it in half. Doesn't really look like it cuts it in half, but we could make a segment cut in half perpendicular. That's the only way we know how to do it. So I need something along this line. I need a segment that when I cut it in half, that halfway cut will go through Q. So in other words, I need a segment that's sort of centered around the zone where Q is. I can get that with the compass. Whoa, how come I'm right clicking? Okay. If I stab here at Q and make my compass reach beyond the line, and I just swing it around, make this little rainbow here, I now have a segment from here to here that has along it a midpoint where perpendicular is going to hit Q. So I just have to do the football on that. So let me stab at one end of that, which is right here. And I make sure this is bigger than half, so let's try that. Okay. Great. Make sure that's going to be long enough. Great. And then the other side of the football, again, stab here. Some people are accidentally stabbing at F or something weird. And I'm just making the football here. So there we go. And then again with my cheater ruler, I'm taking my ruler, invisible ruler, and I'm drawing the football, and it ought to go through Q. I missed slightly, but you can tell if I just move it down. Well, you know what? I can probably fix that perfectly, and nobody will know. Look at that. Okay. Alright, and the next thing says construct a copy of angle Q in the space below. Well, I'm going to cheat and not do the space below because I don't have enough space below. I'm going to do it up here. Would it help if I made a different color for part B? In the space below. I don't mean below, I mean up there. Okay, copy of angle Q. Angle Q, I can start out by just making some random straight line. I really wanted that to be blue so you could tell what I was doing. Okay, some random line. How come it's still not blue? I've changed every possible... Okay. And then I take my compass, so that line there basically is representing this line here. Take my compass and swing some random arc around angle Q. Is this going to be blue? Oh, nice. Okay. I go up here and I need to make a similar thing. I'm constructing a similar picture on this copy. Okay, great. So now basically what I need to do is measure this sort of isosceles triangle's base here, this little span of this angle that's going to make this angle this wide at this depth, sort of. So I can take my compass and measure that. When I say measure, I mean use the compass to do this. So is it right about there? I think I'm really close, maybe a little bit wider. Okay, take that and copy that up here, and that's where I cross this first arc. We haven't done this one in a while, but there it is. So now I have my straight line tool. Yeah. Okay, so that angle has to be the same, and you really need to show this one. This second arc tells us that you know where this position is going, and this position on this arc isn't just an accident. It's exactly there. And the longer you draw this arc, we'll know that it was centered here. We can kind of tell from that. Okay. I have a blank page for no reason. Okay. Construct a parallel. Alright, since we've done chapter 5, this is a little bit easier. What I tried to do on this one is I imagine the fourth corner here of a parallelogram. It would be right about there. If this is going to be a parallelogram, I'll just sketch it here for you a little bit. If I'm imagining somewhere in this zone to find the fourth point of the parallelogram, I know I can find that point by constructing a segment over here that's this same length, and or B and C are already there, constructing a segment down here that's that same length. I'm going to find a point down here that's this distance away from C, and this distance away from A. And all those distances I need are there. Okay, so distances, of course, aren't really something I measure with a ruler, something I measure with a compass. So this point A to C, that's the distance, or sorry, A to B, that's the distance that this mysterious point D ought to be away from C. So I'm taking this, I'm copying it to the other side of the, is that going to work? Yeah, it's a little bit small. Take this distance and I'm copying it over to the other side of the yet to be drawn parallelogram. So D is somewhere along here because it's the right distance from C. And then the other side of the parallelogram would go from B to C. So it's that big right there. It's got to be the same distance down here from A. And once I've done this, I know I have a parallelogram. And I can connect the dots. Whoa, I can right click. I can accidentally right click. I can connect the dots, cheater ruler. Go from C through that point. Oh, it's still blue. Look at that. And that must be parallel to AB because it's the other side of the parallelogram. I've also inadvertently created parallels here from B to C and through that point, but that wasn't the question. This is not the way we originally did this construction. Originally, we had something like this. You had a line and point off the line you're asked to make a parallel. You were told make some random transversal and then copy this angle. We just did copy the angle on the last thing. Copy this angle here. If you copy the angle correctly, you will have made corresponding angles which will make those things parallel. So there's another way to do it. But this is just two little swoops and we're done. This is a lot faster than we know about parallelograms. Okay, that's it for construction, so let's get rid of these tools. Alright, reflect the polygon on the y-axis. Alright, the way to do that is sort of count to the mirror and then flip over the mirror and keep going the same amount. So this little point here, here's the mirror line. People are getting this wrong because they're accidentally flipping over the x-axis. Here's the mirror. Flip this into the mirror, it's going to have to go here. Flip that into the mirror, there's 4, so I got to go 4 more. Right there. And I got to go 3, 3, here we go, and from here, 3, 3, 3, 3, right about there. So there's my little shape right here. Then it says take the image, which would be this guy, and translate it. So each xy point goes to x minus 2, y plus 3. So all the x coordinates are going to go basically left 2 and 3 up. So that's all I do. Left 2, 3 up. Left 2, 3 up. Left 2, 3 up. Oh, right there. Left 2, 3 up. So the new one is, I've been liking blue for my second color today. It looks like this. All these figures should look congruent. And they do. They're just, that might be flipped green. Okay. In this triangle, which one could possibly, oh yeah, this was right off a test. People miss this all the time. Alright, where could point F be? Oh, let's look at these. 0, 2. Sorry, 0, negative 2. Well, the problem is people don't look at this. A, B, C is supposed to go D, E, F. In other words, the CP-CTC is supposed to work the same way. The correspondence has to work out. Now, in this triangle, original triangle, it appears we have an isosceles right triangle. You don't have to know that exactly, but let's just call it an isosceles right triangle for now. The right angle appears to be at B. It's kind of a special one, so the right angle of our new one should sort of appear to be at E. That would be a problem with this one. So that's deliberately there to make you see, oh, that looks like a congruent triangle. It is, but not in this way. So 1's no good. Alright. 2, 1. 2, 1. It's right here. This looks like it might create a right triangle that would be okay. Yeah, I think it's fine. And because the right angle is the right place, these lengths seem to be the right distance. They're around a 2, 3 rectangle. This is around a 2, 3 rectangle, so that's fine. Same thing here and here. The other connection looks like it could be that long, so it's a candidate. Okay. Negative 4, 5 is up. Oop, auxiliary color. Right there. It looks like we have this thing going on. Looks like the same thing just reflected. There's nothing wrong with it being reflected, so that's also fine. So we're looking at D. Okay. 10. The quadrilateral with coordinates bloody blah. Well, it doesn't give you a picture on this, so be careful not to look at this stuff. People are looking at this picture going, what? Makes no sense. Okay. Wow, I have to go to 1, 8. That's really high. 1, 8. Negative 1, 3. Maybe right there. That's 3. That's 8. 1, negative 2 is not as far down as the 3 is up, and 3, 3 is maybe there. Wow, looks like a kite to me, but you probably want to get graph paper out to really make sure about this. The 3, 3 and the negative 1, 3, yeah, they are straight across from each other. And the 1, -2, and the 1, 8, yeah, they're straight up and down from each other, so I know these are perpendicular along the grid lines. This seems to be a lot higher up than this is low, so it's not a rhombus. It must be a kite. Because one's up at 8, and one's at -2, and the midline is... Oh, wait. From 3 down to -2, that's 5. From 3 up to 8, that's 5. Oh, folks. I needed graph paper. That's actually a rhombus. Those diagonals are perpendicular bisectors of each other. That's 5 and that's 5. We already know it's perpendicular. That little part there, this is the midline here, sort of at 1. So this is 2, and this is also 2. So I have diagonals of the thing that are perpendicular bisectors. That means we have a rhombus. Okay. If AF is congruent to AE, then we're talking about a point that's equidistant from, remember these little perpendicular things are the distance from a point to a line. We have a point that's equidistant from 2 rays, or two sort of directions, 2 lines. That means it has to be on the angle bisector. That means this angle bisector is going through that point. So, what special ray? I'll say angle bisector. And it's a theorem. It's a theorem about angle bisectors and distance. I think it's the converse. Yes, in fact it is. It is theorem 4.8. Alright, if B, and let's get rid of this stuff because now we're talking about the next one. In the next one, if BD, this whole thing, is congruent to this whole thing, we have an isosceles triangle, then what is B on? It's on some special line. If it's equidistant from the endpoints of a segment, so it's equidistant from D and C, it's on the perpendicular bisector of this segment. So that, when it goes up here, is going to go through B. So perpendicular bisector of DC. Whoops, it's a DC. I should say angle bisector of angle CBD. Same thing. Alright, by theorem, same thing. There's a theorem about perpendicular bisectors that says if a point's equidistant from both endpoints of segment, it's on the perpendicular bisector. That's 4.6. Yeah, these are 2 of those 4 theorems at the end of chapter 4 that we kind of went over fast, and they're kind of they're interesting. They're a little bit more profound than our normal ones, but we don't use them very often. They're kind of obscure. I kind of like them, but they don't get enough attention. If a line is the angle bisector vertex angle of an isosceles triangle, yeah, this is in the same kind of neighborhood. This is corollary 3 of theorem 4.1, which the theorem is IPAT. What's the 2 things it says? Okay, so if it kind of looks like this, if we're talking about an isosceles triangle and we have an angle bisector here, what does it do in this area? Well, it's a perpendicular to the base, and it bisects base. Those are the 2 things. You could say perpendicular bisector, and that's really one thing, but yeah, the thing is that's fun about this is that happens and this happens if that's an isosceles triangle and an angle bisector. Alright, a triangle can have how many obtuse angles? At most, 1. If you got 2, you got more than 180 degrees, and see you later, you're not a triangle. Am I going to get done with this in time? I don't think I am. Okay. We'll write these as one biconditional. Maybe if I pause. There you go. The thing about... I've got one over here and the rest over here. If and only if is the silver bullet there on biconditional. You write this, it's the statement and its own converse in a forwards backwards sort of way. It puts the original statement and the converse into one sentence. We could have written this backwards and it would have been the same thing. It is homecoming week if and only if I'm wearing pajamas to school on Tuesday. I believe I wrote that question last year when it was a Tuesday during homecoming week and I was wearing pajamas. Alright, provide a counterexample. Alright, a counterexample has to make this part true and has to lead to a false conclusion. If it doesn't make this part true, it's not related at all. I need it to be related. I need to play along at least this long. So I need a number that is less than 2, but is not less than 0. So how about this? Now, a counterexample is not an if-then statement. It's a specific case that applies to this somehow in some true-false sort of way. So a lot of people are going, oh, if x equals -1, then x will... Stop talking. It's supposed to just be this. -1 is a counterexample to this. End of sentence. Fill in the blank with always, sometimes, never. Okay, I got 30 seconds left. I'm almost thinking I'm just going to do another video. Okay, I'll see you in that one in a minute. Have fun.